Problem 94. We have 16 inches of wire from which to construct a square and an equilateral triangle such that the total enclosed area is maximum. So first, let's get a formula for length in terms of the dimensions we have labeled on these two. The total perimeter of the square is 4x. The total perimeter of the triangle is 3y. And this total length of wire must equal 16. Now we want to, since this equation is fixed, this is our constraint equation, we want to solve this for either of the two variables. So I'm going to solve this for y. So we've got 16 minus 4x over 3 for our y. If we look at the total area, this is the area enclosed by the square, which is x squared, plus the area enclosed by the triangle. The triangle is a little bit trickier to see. What we'll do is we'll drop a perpendicular line here. So this half triangle here, the base is y over 2. And now, since this is a right triangle, we can use the Pythagorean theorem to get that the height of this triangle is square root of 3 over 2y. And the area of a triangle is 1/2 times the base times the height. So this is 1/2 times the base now of the big triangle is y, and the height we just computed to be radical 3 over 2y. That means the area inside the triangle is now radical 3 over 4 y squared. Since we've already solved the constraint equation, let's plug what we know for y into the area formula. So we have that the area is x squared plus radical 3 over 4 times this y quantity squared, and that's 16 minus 4x over 3 squared. This is the area, and now that we're down to one variable, we're ready to maximize this. So let's find the domain before we go and find critical numbers. I see that the smallest value we could take for x to have this be physically meaningful is x equals 0. We can't have a negative length for the sides of our square. The largest value of x would correspond to using all of the wire for the square and none of the wire for the triangle. And if all 16 centimeters were used for the square, that means each side would be of length 4. So the domain of this problem is that x goes from 0 to 4. Let's now find critical numbers. We're going to take the derivative of our objective equation. So we've got 2x plus radical 3 over 4. Now for the next part, we're going to use the power rule. So we'll bring that 2 down to the front. 16 minus 4x over 3 to the first, times, applying the chain rule, we have the derivative of the inside, which is negative 4/3. So this is the derivative of the area, and we're setting this derivative equal to 0. If we clean this up a little bit, this looks like 2x plus, now here, this 4 can cancel. So what we're left over with is negative 2 over 9, radical 3. So we're just multiplying all these numbers that are outside the parentheses, times 16 minus 4x. And this must be equal to 0. Now let's distribute this term to both sides inside the radical, inside the parentheses. So we've got minus 32 radical 3 over 9 plus 8 radical 3 over 9x equals 0. Now we want to move all the x's to the same side of the equation and all of the non-x's to the other side. So we're going to move this negative 32 radical 3 over 9 to the other side of the equation. So 32 radical 3 over 9. On the left-hand side, we can factor out an x and then divide to get the x by itself. So 32 radical 3 over 9 over 2 plus 8 radical 3 over 9. This looks like a real mess. So let's evaluate this, get a decimal answer for this. This is approximately 1.74. Now we have to determine whether or not this is a maximum. So we're looking at the area when x is 0. That's the endpoint of our interval. The area when x is 1.74. That was our critical number. The area when x is equal to 4. So in order to do this, if x is 4, it'll be helpful to find the y value. Plug 1.74 into this y formula that we have, and we get that y is approximately 3.01. Now if x is 0, in other words, if we're using none of the wire for the square and all of the wire for the triangle, that means that Our y value is then 16 over 3. So this would correspond to x equals 0. So y is 16 over 3. Now if we plug that into the area formula we have, that gives us for our area approximately 12.32. Now, looking at the complete opposite end of things, here if x is 4, in other words, we're using all of the wire for the square, we're using none of the wire for the triangle, so we're using 0 for the sides of the triangle, and that gives us for our area 16. Now if we look at this middle road here, if x is 1.74 and y is 3.01, the area turns out to be 6.96. Now we're trying to maximize the area. So if we had just gone with x equals 1.74, we've actually sort of found the worst case scenario. This is actually the minimum rather than the maximum. So a maximum occurs actually on the boundary when we use all of the wire on the rectangle. So in other words, our maximum occurs when x is equal to 4 and y is equal to 0.